Hey there, folks. Happy Friday. I hope things have been going well for you. I wanted to complete one more problem before the week finished up, so let's go ahead and do this one here. It's very similar to the last problem, which is why I chose it, but this one is much shorter. So, it shouldn't be too bad. Since it's a Newton's laws problem, we know that the magnitude of F that we need to solve for, well, that's going to come from Newton's second law. And here's our vector equation that we've seen dozens of times at this point. What's nice here is that the force we're applying is entirely in the horizontal direction. So we don't really need the full vector version of this equation. Let's exchange it out for the scalar version. One thing we need to be careful about, though, is that we can't use a single mass variable here, since we're essentially pushing the sum of two masses. So let's go ahead and switch this out with the sum of two masses, like this. All we need to do is figure out what the resulting acceleration would be, okay, this lowercase a here, and then we know F, and we're done. For the sake of showing all of our steps leading up to the answer, let's begin with the free body diagram of the wedge. Most of the approach doesn't change from how we did things in problem number 27. The coordinate axes stay the same, and in the y direction we still have the weight of the wedge and the normal force from the tabletop canceling each other out. In the x direction, our familiar reaction force vector r is still here as well, but now we have to include the applied force of us pushing directly on this wedge. You'll still want to include r's angle and break that vector down into its components. This time, the acceleration of the wedge will point to the right in accordance with the force that we're applying. Next up is the block. The weight of the block and the opposing reaction force from the wedge are still there, but now we need to adjust our fictitious force to account for the change in the wedge's acceleration. That means that it's going to point to the left this time. Go ahead and toss in our angle and break things up into components like before, and that's it. There's no need to include an acceleration vector here, since this fictitious force that we're adding will take care of that business for us, as you'll see shortly. Time for the sum of forces on the wedge. In the x direction, we have a single line that can't be simplified any further, so let's take a look at the sum in the y direction. Unfortunately, there's not really anything helpful here either. Everything balances out since the wedge doesn't accelerate up or down relative to the tabletop, and if we solved for this normal force or the reaction force, it wouldn't put us in a helpful spot for solving for lowercase a here, since we have no idea what F is yet. Ultimately, that's what we're trying to figure out. So let's move on to the block and see if it has anything useful to share. Starting in the x direction, we can see that the sine component of the block's weight will be canceled out by the cosine component of the fictitious force that we added. Since there's only two terms here, well, we can try algebraically solving for lowercase a and see what we get. First, I'll move the cosine component of that fictitious force over to the right-hand side. Then I'll exchange the weight of the block with its definition, mg. We appear to be on the right track since there's mass on both sides now. Let's cancel that out. Next, if we divide both sides by the cosine of alpha, we do end up with an equation for lowercase a. Sweet. Let's go ahead and do one more step and exchange sine over cosine with tangent. Now this is what we needed. Let's go back to our scalar equation of Newton's second law to get the full magnitude of f and be done. Here's what we had on the problem description slide. If I plug in what we just solved for lowercase a, well, this is all we needed to do. The problem is done. Not bad at all, right? Thanks for watching, guys. Have a safe weekend.